today Professor Ralph Showalter from Oregon State University. Professor Showalter graduated his Bachelor's of Science and Master's in Mathematics from NC State University. And then he went for his PhD at University of Illinois, after which he held a Blumberg Centennial Professorship in Mathematics at University of Texas at Austin, after which he moved to Oregon State University. He is the author of two wonderful books in PDEs, and I have to mention one on Hilbert space methods in partial differential equations and one on monotone operators in Banach spaces and nonlinear partial differential equations, which I strongly recommend to any graduate student in PDEs. And now, Lord, all you.
Thank you, Lorraine. It is a pleasure to be here. I'd like to take this occasion to share with you some of my experiences in moving between analysis, functional analysis, and PDE. The motivation for learning functional analysis was because the PDE was so damn hard, and I couldn't figure out what the common themes were. Let me start with the following. A theorem, of course. I won't write a lot of these down, and this is not typical of what's coming, but I wanted to start this way. Let's let V be a Hilbert space, Q another linear space, normed linear space, not necessarily complete. I have a function E on the product of those two, so it's a bilinear function on that product, and with the property that if I fix the right variable, I have a continuous linear function of the first variable. So it's continuous on one side only. The theorem is this, given those in that background. Whoops. If this if soup condition holds, by the way, what does this say? Reading it from the inside out. Soup over V. That means I'm computing the norm of the dual E prime at phi. If that is bigger than or equal to C times the norm of phi for every phi, that's what the if soup condition's telling us. If the E prime, the dual operator, is bounding. It's bounding the Q norm of phi. If that's true, then for every linear function on Q, there exists exactly one solution of this equation. There exists a solution, U belonging to V, E U phi equals F phi for all phis in Q. By the way, this will be the form of certain PDE problems. Not only those, but certainly some. It's so what I'm calling, so I'm going to come to, so the if soup condition implies that the equation always has a solution. And there's more coming with that. Most important is the proof of that result. It's elementary. Let me just talk you through it quickly. Just show you that outline of it. And really the outline is really the proof. Since that form E is continuous in V, that means for each phi, I can write this as a linear function on the V's, the action of that linear function on those vectors V. So the K then is defined. The K is not necessarily continuous itself, because the E is not continuous in the phis. So the K need not be continuous, but we'll see something later. I can use that K if the K is 1 to 1, which will follow. The equation I want to solve looks like this. So for every test function phi, looking at it, if this is the phi, this is the K of phi over here, and that's my E of U phi equals F of phi. So my original problem, the equation, appears in this form right here. I've just rewritten it that way. But the if soup condition, I said, makes the dual operator related. That if soup condition is equivalent to saying if the K phi is bounding, okay, so it has an inverse on its range, on the range of K. K inverse is defined on the range of K, gives me a function into Q, and that extends uniquely by continuity to the closure of the range. And I'm going to note that with the bar on that. And that extension will necessarily carry me into the completion of Q. That's okay, this is sort of abstract at that point. I don't really care what that is. What I need to do is extend from the range of K to all of V. Well, if I'm in Hilbert space, I have a natural orthogonal projection from V prime into the closure range. If that's a projection, then my equation is a consequence of, that is, it follows from this identity over here, because P is the identity on the closure of the range of K. So my original problem looks like this. But aha, that makes it easy, because this operator right here is continuous and linear, it has a dual, and this line says that U is equal to that dual of this guy acting on F, and I'm done. And that's my solution. Okay? And by the way, since the solution I've generated here, or found, was given by a continuous dual, that solution is bounded by the data F in the problem. So I have found a solution which depends continuously on the data without the assumption of uniqueness. There are many, many different ways I could have extended that. I used the projection P to do the extension, but there are many ways I could have done that. So there's much, much non-uniqueness in this problem, potentially. Okay. So what? That's the proof that was given by Jacques-Louis Lyons about 61. But he did it for the following special case. He was assuming that the space Q is continuously embedded in V, and that the E satisfied a coercive statement. That's kind of like a positive definite statement on that one. By the way, the in-soup condition in the finite dimensional case is exactly one of the classical theorems of linear algebra, which relates the solvability of the system to the kernel of the dual matrix. But in this special case here, where this essentially saying E is, in the finite dimensional case, we're saying it's positive definite, we're calling it a coercive statement, then the in-soup condition is a consequence of that. This was the context in which Lyons first gave that proof. And a dutiful student can go through the proof and realize that it works in that more general case. An even more industrious student might also observe that if the equation is solvable for every f in the dual space as indicated, then the in-soup condition also holds. In other words, it's if and only if. As stated originally, it's actually if and only if. Corollary to that, well, with Q equal to V, had classically been applied in many, many places to solve linear elliptic boundary value problems. This was in the work with Lax Milgram in 54, Lyons himself, 53, 10 years before that, and Mikhail Vishik in 51, thereabouts. So in the early 50s, this result, in the special case I indicated here, which would be a generalization of the Lax Milgram theorem, that was used extensively for elliptic boundary value problems. I cared about it because you can also use it to solve evolution problems, unlike the original, the special Lax Milgram theorem. Let's apply to this example here. Suppose I want to solve this really simple equation, u prime plus u equals f. And I want to ask, what does that theorem tell me about that problem? Well, let's see. Let's make it a weak problem here. Let's get rid of that derivative here. I'll multiply that by a test function phi, integrate that derivative over onto the test function, and then I'm looking at this e of u phi on the left side becomes this quantity right here after I do the integration by parts. So my equation comes over on the test functions in this form. And my right side was just the f multiplied by phi, and when I did that integration by parts, I picked up a term involving the initial condition, and to make sure that I did not see anything at the final time, capital T, I apply this to test functions, which are in H1. That means the function and its first derivative belong to L2. So it's an absolutely continuous function with derivative in L2, and which vanish at the endpoint. If those are my test functions, I don't see that other thing. And in fact, EU phi equal f of phi for every phi in here is exactly the statement of that problem up there. That's just a weak form of that. Well, this theorem tells me, not surprisingly, that initial value problem always has a solution. Interesting thing to come up here is Q, the space, V is a space L2, that's where I'm going to look for my solution in L2 initially. By solving the equation, I'll find out that the derivative also belongs to L2. That's not part of the problem. I was looking at a weaker part of the problem. My space Q, and that has its own norm associated with it, which I can't really mess with. The Q, I have some choices here. Q is this space, and then the natural question is, what norm do I put on Q when I apply the theorem? Well, let's see. What happens? E, this E here refers to, if I compute E of phi and phi, you have to remember what the E was there. If I look at that E of phi and phi, I evaluate it, I get this expression right here. This guy is always coercive over L2. So it seems like L2 norm is a natural input on Q, and that means I can choose my data out of L2, and the problem always has a solution. Okay, fair enough, certainly true. But if I look carefully at the K that I had in my proof, in this example, that K is just phi minus phi prime. That's what we saw acting on the test function in our calculation. If I compute the L2 norm of K of phi, so I square that guy, then integrate it. That guy squared gives me a piece, the L2 norm of the function. This guy squared gives me the L2 norm of the derivative, which is the H1 norm. And I have left over from the intermediate part, I have phi at 0 squared. The important thing is this guy here. That's a much stronger norm than the L2 norm that I mentioned before. So that theorem applies when Q has a much stronger H1 norm, which means I can choose much more general data and still say that there exists a solution to the problem. Right? So the point is that this theorem does give me a proper extension of what I would get out of the earlier version of this theorem, and certainly the original Lax-Milgram theorem did not apply to this at all, because there the two spaces had to be chosen the same for it to work. Okay, so this could be something positive. Anyway, the bottom line is that these ideas and a lot of technical background allows you to use that theorem to solve a lot of parabolic problems, in particular for general operators representing elliptic equations like so. So this becomes a parabolic initial value problem. So that theorem allows you to solve lots of parabolic problems. That was the thing I was trying to get in such a setting. We knew how to do elliptic problems. How do we do the parabolic ones? This was a way to do it. This was mostly the contribution of Lyons and co-workers. Lyons was pushing it to the evolution equations. Other people were concentrating more on elliptic equations. Afterward, I pushed some of these ideas and was able to push it to cover not only the standard evolution equations, but also those with a pair of linear operators, both B and T. The B and T could be given independently of each other, and you could solve problems where you had a pair of operators, and that opened up a lot of possibilities which had not really been developed very much at that time. But the point is, they all came out of the basic ideas of that simple theorem and that little example that we saw there. That there was a lot that came out of that. But I really want to go back to this inf sup condition. Some other related theorems. Notice the dates on these. Lyon's theorem was 61. These were in 71. Lyons was doing it to solve evolutionary equations. These guys were doing it to solve numerical analysis problems. More about that later. From the names, you can kind of tell where it's coming from, but you have a pair of spaces in before. We have an operator B mapping continuous linear from V to Q prime. Then with B is an I have equivalent conditions here. B is an isomorphism. That statement is equivalent to that pair right there. This one says that B prime is bounding. This one says that B is bounding. If both of them are bounding, okay, then the operator B is one-to-one and onto.
So the theorem does not require the space to be Hilbert space.
Pardon?
It doesn't need to be Hilbert space. It can be a balanced.
Yes. It doesn't need to be. Doesn't need to be, no. No.
But you
It's
define-
going to get better. It's going to get better, right. But this is a theorem that was given in 71.
Oh, that's it. I didn't guess.
And that statement's going to get more interesting in a minute. So in 71, we had this pair of statements, Natchez and Babushka. They were working on finite element methods. This was fundamental to getting stability estimates. That C in there is the stability constant. About the same time, Babushka pushed a little further and got rid of the bounding statement. This one is still bounding, but this one here is just strictly positive. Okay, it's 1-to-1. This one says here that the B prime is 1-to-1, and that's enough to make B onto. Okay, and the other condition makes it 1-to-1, et cetera, et cetera. So these are the sorts of things that were being done in 71. Let's backpedal 40 years. Closed range theorem of Banach. The usual statement that you see, the range of an operator is closed exactly if the range of its adjoint is closed. Okay? You go through the proof, and what that gets down to is saying that the range of B is the annihilator of the kernel of the adjoint, and the range of the adjoint is the annihilator of the kernel of B. Those are four independent but equivalent statements. Okay? The most interesting part of all is that each of those statements is equivalent to corresponding in-soup conditions. This condition by itself is equivalent to each of those others, and likewise this one. Okay. Slight difference there, we factored out the kernel of B in that one, factored out the kernel of B prime in that one. But that in-soup condition is equivalent to closed range on either B or B prime, which are also equivalent statements. So those are six equivalent statements, which subsumes most of the theorem we've seen before this. Okay? No comment, just passing it on. Okay? Why do we care about these things? The bilinear forms and elliptic problems. Start with the Hilbert space, continuous, linear, and symmetric operators. Suppose script A there is not only continuous and linear, but symmetric. And I want to solve this equation here. Of course, that would say that AU against V is equal to F at V for every V belonging to V. So that looks just like the statement we had before. This is a very special case of what we were looking at before, with the V equal to the Q. That equation is actually equivalent to a minimization problem. If you define the quadratic function, 1/2 of AVV minus the linear part f of V, if you minimize this quadratic over the space V, that minimum occurs exactly where the derivative of phi is equal to 0, but the derivative of phi at the point U is exactly this guy minus that guy. So that's just a statement that we learned about minimizing a quadratic to solve a linear equation. Okay? And it's also the minimum energy characterization of the solution of Dirichlet's problem. That's the association with elliptic problems. And in fact, for much of the existence theory for elliptic PDEs. And there are approximations by various methods, including finite elements. Okay? You minimize over your favorite finite dimensional subspace to get an approximate solution, etc., and that's your starting point. But anyway, the minimization problems are characterized by these operators A. In the case where the A is symmetric. Change the problem a bit. Add a constraint. Suppose instead of minimizing that same phi over the whole space, I want to associate another constraint. The constraint I'd like to impose is I want to find a solution for which B of the solution equals G. Well, as a way to start off, for example, let's just minimize this guy plus this penalty term. Let epsilon be your favorite small number, and minimize this quantity. This guy tries to get small, but he wants to do it and try to keep this guy small, but if epsilon is small, that's going to force B of V to be close to G. And you can kind of guess what's going to happen when the epsilon really gets small. In particular, if I compute the derivative of this guy, to find out where the minimum of this one occurs, its derivative is given by this quantity here. And then, if I cleverly chose this piece here, if I rename that to be P, is that done? So let P be this quantity right there, and I've got AU minus F plus B prime of P, where P equals this, there's C of P, et cetera, et cetera. I'll summarize on the next page where we have them written again. Here's my statement with A, here's my statement with B. That's just, this was a definition of P right here. And those two statements together are that system. So that minimum of that epsilon problem is characterized by that system of equations. And from here, it's even easier to guess what happens if epsilon is 0. If we let epsilon go to 0 here, we lose that piece. Our system looks like this. And this is exactly what we would get if we had just gone straight ahead and minimized the original phi of v over the linear space, over the translate of the linear space of v's for which b of v is equal to g. In other words, minimize this over the constraint set, we get exactly that system. So when I went, if b is equal to 0, there's nothing to do there, it's just a of u equals f. But if b is the constraint go into it, b of u equals g, in order to attain that constraint, I have to give up something. And what I give up is this piece here, because this is no longer equal to that. And that p is my Lagrange multiplier that allows that constraint to be satisfied. Okay. An old subject, so we're trying to use that to motivate where we're going. Instead of solving a single equation, AU equals F, I want to solve a system. This system generalizes the original one, that single equation. In particular, allows me to put constraints on the solution, obviously, that's where we got it. More important, when we're modeling, building models of things, in fact, the way many models come up to us originally, they're given to us as a pair of equations, a conservation law and a constitutive law, and that pair of equations we can identify with those two in that system I had. But that system allows us to keep the essential variables. I don't have to eliminate one variable to get a higher order equation for a single variable. I don't have to do that. There's already a theory to take care of the system. I don't have to fudge around with it to get to a single equation. More important, for the point of view of building models, there's much more versatility in this formulation. I have what? I have 2 spaces instead of 1 to work with. I have 3 operators instead of 1. There's much more versatility in that system, and the theory for it is really not that much different. Anyway, so there are lots of reasons for looking at these systems instead of a single equation. Let me go back to, well, let me give the following theorem. Lax-Milgrom theorem says you can solve a single equation even if the A is not symmetric. In this minimization problem, I was assuming A was symmetric. I can drop the symmetry condition on A even in that system. Here's one example of such a theorem. If I given the A and the given the pair of operators A is okay. I got 3 operators A, B, and C. There are no only C is required to be symmetric. Certainly not B, and A need not be. In particular, A need not be symmetric. In spite of that, if I have this if soup condition on B, and if A is V coercive, so it behaves like an elliptic expression, but on the kernel of B, that means that A plus B is somehow bounded. So A is coercive, not everywhere necessarily, but at least on the kernel of B. And with the other others given as such. If I have the if soup condition on B, then for every pair F and G, I can solve that system. This is sort of the analog of the Lax-Milgram theorem. Special cases of this worth mentioning historically. In the case where C is equal to 0, and by the way, the C is this operator here. Notice the diagonal terms here. You'll see the system in a number of places, number of ways. For perspective, notice that the way it's given is the way it comes up naturally in the minimization with constraints. If I multiply through the second equation by -1, you'll see I have A and C being non-negative operators on the diagonal, and a B prime and a minus B on the off-diagonal terms. That's recognizing the symmetric part of the diagonal and anti-symmetric off-diagonal part. That's a useful way to think of that system.
What C is must be symmetric?
Pardon?
What C was symmetric seems.
Because this was the form that was done at that time.
So really the same for A.
I can't remember actually when I relaxed the C symmetry. I'll watch it. Certainly if C is 0 and A is V course over the whole space, then the corresponding existence result was done by quite a few people coming from different directions for lots of different reasons. Also, when C is equal to 0, if we have the if soup condition and A is kernel of B coercive, this is equivalent to solvability, and this was noticed by Retzi in '74. And in fact, all of this material is written up nicely in the book of Retzi and Fortan in 1991. Not real long ago. And I want to tell you today that the existence theorem for A and C nonlinear, and in fact the corresponding result for evolution equations, is also true. Let's look what we mean by that. It gets a little technical to say it, but here we go. We have this is not the most general case, but certainly adequate for most applications, the kind I'm thinking of anyway. We have a pair of real Hilbert spaces. We have a pair of operators E1 and A mapping V to V prime. Now a pair of operators E2 and C mapping Q to Q prime. The A's and the C's are not linear. E1 and E2 are linear. The B is linear from V to Q prime. Okay? And there are some other assumptions in here. I'm not going to dwell on a lot of these, but suffice it to say that this certainly covers the linear case we had before, and an awful lot more. And where we end up is with the statement that, this is for the stationary problem, is that this system, this resolvent system here, I'm calling it result, I'm anticipating something here, this system always has a solution. This is the piece we saw before. Notice I multiplied through that by -1. That's the system we had before, and we can also add these other operators over here. I have reasons for doing that. And some of the hypotheses on the E1 and the E2 allowed me to relax some of the conditions on the A and the C. In other words, certain hypotheses hold for the pair A, E1, and for the pair C, E2. The most important thing is the A and the C can be nonlinear. They don't have to be subgradients. They are nonlinear, and in fact, they can be multi-valued. It suffices for them to be maximal monotone operators. Very general situation. In fact, the corresponding evolution equation looks like this. And now I have time-dependent problems where the E1 and the E2 are out here with time derivatives on them. So now I have a pair of evolution equations. This is roughly the, okay, so those are the diagonally dominant parts. Those are the off-diagonal antisymmetric parts. I know some time derivatives. The important thing here is that there's nowhere in this thing that requires E1 and E2 to be anything except non-negative. Either or both could be identically zero. Either one can be non-zero. So I could have a time derivative in the top equation, a time derivative in the bottom equation, or time derivatives in both, or time derivatives in neither. Okay? So the real strength of this result here is the fact that that E1 and E2 are only required to be non-negative and symmetric. That allows lots of PDE type applications. All right. And basically the idea is to use E1 and E2 to construct a pair of spaces in which solutions of this correspond to semigroup generation theorems, and to apply the nonlinear semigroup generation theory. That's sort of a two-sentence summary of two-chapter.
So you said you reduce the norm
Pardon?
on U and C by E1 and E2.
Use the E1 and E2 to construct semi-norms.
Then
Right. And then basically do the evolution in those spaces. So the evolution takes place in the dual of those semi-norms, which of course is the open space. The dual space is always complete.
but you should get stronger. Parabolic.
Yes. Yes. Well,
Because you
It's
assume strictly one.
okay, it's generated by a maximum monotone operator, but
But
it's not
it's a-
necessarily parallel.
I understand. Still stronger than
Yep.
the normal.
It's the time, it is a time dependent formula. But the evolution takes place in that
And-
product of the open
I
spaces.
understand.
Some examples. Let me do this first one slowly. I'm talking about fluid flow through a porous medium. So I've got something like water flowing through the ground, crude example, right? It's driven by the pressure gradient. That's the Darcy law right here. If U is the velocity of the flow, okay, it's reciprocal permeability and viscosity, building that, etc. Anyway, the fluid velocity is proportional to the gradient of the pressure, and that proportionality is summarized in that coefficient A. Okay, that's the Darcy law. That's a constitutive equation. That's the conservation equation. The divergence of the velocity is given as the source terms. So there's my conservation law, there's my constitutive law. And I've named these to look like the variables I had in the equation down here. The operator A just means multiplication by the coefficient A of x. Very nice operator on L2. B, or B prime is my gradient, and B is the divergent minus the divergence. So my system, AB prime minus B, is exactly the Darcy system written this way up here. My two equations correspond respectively to the constitutive law and the conservation law. This is a mixed formulation for the problem. And by the way, in our introductory courses, the first thing we do is that we eliminate the velocity u, back substitute there, and get a single equation for p, which basically substituting this u into that one tells us that minus the divergence of a of x times the gradient of p is equal to f. Okay? If a is equal to 1, that's Laplace's equation, and we're off to solving a Dirichlet problem. Or Neumann. Poisson's equation for some boundary value law. This is written choosing B, where do we have it? Right, choosing B to be the divergence. This is sort of nitpicking here, a way to get fancier boundary conditions, and I don't want to dwell on that. A different way to do it, I did it before with the gradient operator. This time I do it with the divergence operator. I define B this time with the divergence operator. So that's my definition of B. And the B prime turns out to be the gradient plus boundary conditions. I can get the same problem and write it on this. Looks the same, but it's really a different problem. The way they're different is the boundary conditions that come along with them. So I'm taking advantage of the spaces involved, the changing of spaces on which those operators act. I get a different family of operators. Here's a cube game. If I do an interface problem, I have a Darcy system here, a Darcy system here, and I want to couple them together. The interesting part of this thing is what happens at the coupling. If I write one of them in the gradient formulation, the way I did first, that's the system with the coefficients A1, etc. I write the second one in the divergence formulation using a divergence operator. The equations are the same with the corresponding coefficients, but the boundary conditions that come along with them are different. In the gradient formulation, I had the pressure given on the boundary. In the divergence formulation, I had the normal flux given on the boundary. Okay? And now on their common interface between the two regions, I get boundary conditions of this type. In other words, the pressures don't have to match up, but they can differ by something involving the normal flux. Likewise, the normal fluxes don't have to match up because they can differ by something involving the pressure. There are situations when you would like to solve that rather exotic-looking interface condition, but you can't do it with any one of those problems by itself. You have to use the pair of them. It's a straightforward computation for experts, but it seems to have been overlooked and certainly not used. At least I've never seen it used before. People doing flow in the neighborhood of fractures and interfaces sometimes have to worry about conditions like this, and it becomes a hard problem. But this shows here in this formulation, it's an easy problem.
You mean alpha and gamma is physical? Alpha and gamma is physical mean.
We can specify those, right? The alpha and gamma we can specify any way we want. Those were the C operator.
And alpha, beta,
Let's see, so the gamma might appear with a concentrated capacity on the boundary, and the alpha would be a resistance on the boundary, on the interface. And if I'm doing the time-dependent problem, it could be time derivatives, and especially with the gamma term. So you want to have a rate of accumulation of something on that interface. That would be the concentrated capacity. Okay, here I just wrote down the stationary problem that comes out of that evolution. So anyway, so the point is, this is just sort of one example to illustrate that with this fancier system, it works right away to give you solutions to problems that were considered relatively difficult. Anyway, so I'm just summarizing here. The interface conditions are achieved by either of those only. You can't get any of those with a classical formulation, by the way. In that problem I just showed you, I have never been able to find a way to set that problem up appropriately as a single operator equation on a single space. I've never been able to do it. I've tried a number of times, and never managed to do it. There are similar remarks we can make about the Stokes system, and I'm going to skip over that. Basically, you can have a gradient formulation, a divergence formulation. They really do give you different types of boundary interface problems. They all have good meanings, and not surprisingly, because they come out of those constitutive and conservation law, so it's not surprising they have a physical meaning, and those really are the conditions that one would like to have in the problem. And one more I want to start with here. This is the Darcy-Stokes problem. This is actually a relatively newly done problem. I have a Darcy system, porous media flow on one side, but adjacent to it is a free fluid. I'm going to take the simplest case, not the Navier-Stokes, but I'll take the simple linearized Stokes system. So it makes I have a free fluid on one side of an interface, and on the other side I have a porous medium. And they're coupled along that interface. And actually, I could solve either problem by itself in lots of different ways. And now the challenge here is to do it as a combined system, to do it all as one. So to set up notation, so I have two parts of my region, omega 1 and omega 2, and they share the interface gamma. The first one is the saturated porous matrix structure, and the second one is the adjacent open chamber, each of which is fully saturated. The fluid velocity on the other side are denoted by U1 in the Darcy region, U2 in the fluid on the right. I guess left and right has no meaning here, it's just 1 and 2. And I denote the corresponding pressures by P1 and P2. So I'm using the superscripts to tell you whether I'm in omega 1 or omega 2, either in the porous medium or in the free fluid. And if I write down the systems for each, in the porous medium, if you ignore this term right here, just throw that one away. There's my constituent assumption, the Darcy flow. And it could be nonlinear in the velocity. So the velocity is related in a nonlinear way to a gradient of a pressure. So that's a nonlinear Darcy law. The conservation law is written this way. This is the rate at which fluid can accumulate at a point where the fluid is slightly compressible. There's a divergence of the velocity, and then there's a possible extra storage term over here. You can set that equal to 0 if you wish. That depends on the pressure. It's a compressibility term again, and then a forcing term. So anyway, this is a more general system. And by the way, this more general Darcy law is sometimes used, not very often. Most of the time that's equal to 0. But if you think back to the theorem, the evolution theorem I mentioned for the system, where those two operators there have to be linear and non-negative, that means the requirement here is that rho 1 is bigger than or equal to 0, and C1 is bigger than or equal to 0. Those are the only constraints on those two coefficients. This guy has to be a monotone function of U, that's a monotone function of P, and those are the fixed gradient and divergence, which come with the problem, and we can't change those at all, and wouldn't want to. The Stokes system, we can write in the following form. The velocity satisfies this conservation law. Okay? What have I got here? So, anyway, so my Stokes system is written this way. And, okay, so that's the gradient on that vector velocity here. So that's, this is sort of this is like a nonlinear Laplace term here on that velocity. And there's my gradient of pressure. So this one is, again, allowed to be nonlinear. There's my conservation law plus possibly a storage term. And now the interesting thing is that what comes out of this, with this setup, what comes out of it naturally are these interface conditions, which are exactly the ones you have in that problem. So the velocities have to, the normal component of velocities match up, the stresses match up on the two sides.
C2 cannot be 0.
Pardon?
C2?
C2 can be 0.
Can be
Yes.
0.
C2 can be 0, for sure. Right. So again, rho 2 and C2 are required to be bigger than or equal to 0.
Or equal to 0.
So I match up normal velocities, I match up normal stresses, I match up tangential stresses, and those are my three conditions on the boundary, which are the natural ones. The linear version of this problem was done by Leighton, Schwabik, and Yotov in 2003. And you can just as well do the nonlinear version using the theorem I just quoted you before. And we fix this one off right away. Actually, more than that, you can use this theorem to, now I'm going to skip over this section here. If that porous medium we were talking about was something like a sponge, if it were a deformable porous medium, then I would also have some elasticity type equations to describe the motion of that sponge in addition to the fluid that's moving within it. This is modeled by the standard, I get to it, BO system of pore elasticity. This is a special case over here, where I had before the rigid porous medium. You can just as well have a elastic porous medium adjacent to a fluid. And you can also solve that one using the theorem I quoted you before. It fits right into that frame. And again, the whole point is you just have to be careful to write those out. Let me put it back up. The utility of that theorem is if you write your equations out in the natural form in which the conservation laws arise and the constitutive equations arise, and if you don't screw it up by eliminating variables and try and get it into a format that you recognize from somewhere else, if you leave it the way it was given to you, that's the way it will fit into that theorem, and you get to the result that you want. Okay. Sorry, I got a little technical at the end. We skipped over a lot, but I'm trying to make the point that well, for example, when we give our students a 3x3 linear algebra problem, okay, the first thing we want to do is eliminate two of the variables, okay, end up with a problem with polynomials, which is much harder than the one they started with. They've sort of destroyed the original nice structure of the problem. So what I'm saying is, here's a theorem that allows you to solve it in the way that came to you as a very natural structure all its own. Don't mess it up. Take it the way it is. Thank you.
Any questions?
So,
In your Stokes system, you buried the viscosity somehow in the epsilon operator?
I'm sorry?
In your Stokes system, you had in your second equation, you had a nonlinear operator, but really that should be a viscous term.
Right. Just right. It's a viscous term. Right. It's a viscous term. Naturally, the easy cases where the nonlinearities are in viscous terms.
Yeah.
Right.
Because it's mid.
That's the correct observation. Usually viscosity just makes things better, even if it's nonlinear. Usually.
If there are no other questions, let's thank Professor Showalter again. And if anybody would like to join us for dinner tonight, please let me know.